Good morning, everyone. My name is Keira Proctor, and I'm the Managing Director of the A. Proctor Group, and this is the 11th of our webinar series, which has been running since the beginning of April. We've covered a lot of different topics, from building on contaminated land to roofing and everything in between. If you've missed any or you're joining us for the first time, you can go back and view all of them on our website at www.proctorgroup.com or on our YouTube channel. Today we're going to take a look at self-building and cover some of the basics of construction practices and terminology across the entire building envelope. I completed my own self-build project 2 years ago, and even working in the industry, there's still a good learning curve to negotiate undertaking any building project yourself. So we're going to start today by looking into the various ways you can undertake a self-build project and how hands-on it's necessary to be as a client across these approaches. We'll then discuss some of the factors involved in the building warrant processes and introduce some of the basic building physics involved in houses. From there, we'll go through the anatomy of a house from foundations to roofing and look at some of the key decisions required at each stage and what the implications of those are. There are as many different ways to self-build as there are self-builders, so throughout today's presentation we'll be generalising a little. Aspects such as financing, plot choice and planning are very individual, so a little outside our scope. We'll therefore start with how to manage the delivery of the project, and here there are a few options. The least common option, but by far the simplest, is to appoint a design and build contractor who will undertake the entire process from start to finish. This simplifies the project by limiting the processes the client has to undertake, but can have higher costs. In theory, however, these costs are less likely to vary, and any issues that arise along the way are the contractor's problem to deal with. Most self-builders, however, want to have a greater degree of involvement in the process, as this is often a large part of the reason to undertake a self-build project in the first place. In the majority of self-built homes, therefore, clients take on at least part of the project management process, coordinating the design and build process themselves in partnership with architects and contractors. Within this, there's a range of ways to manage the project. At the most involved end, clients manage the entire process dealing with planning, building control and architects on the design side, then appointing and managing the individual trades directly. This fully hands-on approach is perhaps best undertaken by people already familiar with the construction industry, but it does offer the maximum possible flexibility in the process. For those unfamiliar with the process, however, it can get easily out of control, leading to higher costs and longer timescales. A common middle ground approach is therefore to work with an architect on design and compliance, and then appoint a main contractor to manage and deliver the project on site. This is what I did. This does make it more difficult and expensive to make changes to the specification and alter the project, but streamlines things a great deal as those delivering the project are familiar with the processes, regulations and technologies involved. Finally, there is the option of a kit house, produced by a timber frame or structural panel manufacturer. These are off-the-shelf design that can be supplied and erected on site with minimal modification. Typically, these are supplied as a wind and watertight shell and will usually have various standard options to meet building regulations. While this approach gives a degree of flexibility over aesthetics, it doesn't always allow a lot of scope to alter the fundamental layout of the home. Balancing the flexibility given by managing the entire project against the time and expertise needed to do this effectively is the key to a successful self-build project. The building regulations exist to ensure that not only buildings are safe and robust, but also that the built environment contributes to wider policy objectives such as energy efficiency. There are 3 sets of similar but subtly different regulations across the UK, covering England and Wales, Scotland and Northern Ireland. While some of the specifics vary, the general thrust of the regulation is similar, and they all reference a lot of the same research and guidance. In the Republic of Ireland, the building standards also share some of this guidance, so the general principles apply there too. Today, we're going to be mainly considering the sections of regulations relating to energy performance and moisture control. Energy performance, which includes both insulation levels and air tightness, are addressed in Part L of the England and Wales regulations, Part 6 in Scotland, Part F in Northern Ireland, and different Part L in the Republic of Ireland. In all 4 cases, the energy use of the building is assessed holistically, with all factors such as air leakage, insulation levels and heating efficiency considered together. In all areas of the UK, this is done via SAP, or Standard Assessment Procedure calculation. In the Republic of Ireland, a different process called the Dwelling Energy Assessment Procedure is used, but the concept is similar. While the same procedure is used across the UK, there are some important differences in how the results are applied and what limits are set in certain areas. So a building or building type designed to Part L regulation may not comply with Section 6 and vice versa. It's important, therefore, when choosing designers and suppliers that they're familiar with regulations in the specific part of the UK where the project is based. Condensation and moisture control are covered by Part C for England and Wales, Section 3 in Scotland and Part F in the Republic of Ireland. Northern Ireland is also Part C, but it's a different document from that applying to England and Wales. As regards to controlling condensation, the relevant causes in all of these regulations refer the specifier to BS 5250, the Code of Practice for Condensation Control in Buildings. This means that wherever in the UK or Ireland the building is, the applicable design principles in terms of minimising the effects of condensation are more or less the same. So we've seen the building regulations revolve around keeping buildings safe, warm and dry. To put this into context, it's important to understand some basic building physics relating to heat, air and moisture movement, starting with heat transfer. In terms of energy performance, managing heat transfer is the most obvious consideration in our design process. There are three basic modes of heat transfer that are present in all buildings to some extent: conduction, convection and radiation. The simplest way to illustrate all three is heating a pan of water on a hob. Conduction happens where two objects are in contact with each other, like the base of the pan sitting on the hot plate. This direct contact lets the heat flow from the warmer hot plate to the colder pan, until either temperatures equalise or the pan is removed. Most building insulation boards, such as mineral fibre or polyurethane, work to resist heat transfer by conduction. Convection occurs when heat is transferred by a fluid medium, which in buildings is usually air, but in our example here is the water in the pan. As the water at the bottom of the pan heats up, its density reduces, and the warmer water will rise relative to the surrounding cooler water. The cooler water then sinks to take its place, setting up a circulation of water known as a convection current. As the temperature of the water becomes more uniform, the speed of this current will reduce. In buildings, convective heat transfer can be minimised by ensuring good air tightness is achieved, restricting this circulation from happening. Radiation is the transfer of heat from one material to another, which occurs by means of electromagnetic waves. Radiation does not require either physical contact of the materials or a fluid medium. A warm surface such as our hot plate will emit infrared radiation, which can travel across a space even in a vacuum. When these infrared waves strike another object, they are converted back into heat. The efficiency of this conversion process is governed by a property called surface emissivity. The lower this value, the less able a material is to absorb or emit heat via radiation. In construction, reflective foil membranes and foil-faced insulation materials can help limit heat transfer by radiation. To quantify the heat loss through parts of a building, we typically talk about U values. These are derived from the thermal conductivity of each material in the elements, along with its thickness and a number of correction factors. We've gone into this in a lot more detail in previous webinars, so if it's of interest to you, you can go back and take a look at these to learn more. For now though, what we need to understand is that U value measures the rate of which heat flows through the elements, so the lower the U value, the better the insulation performance. The more insulation we add to a construction, the more we reduce the U value. But this is not a linear process. As U values get lower, the amount of insulation we need to add to improve them further increases exponentially, so it's not always practical to keep piling in insulation. We therefore need to think about what else we can do to optimise the energy performance of the building. The first thing we can do is limit what's called cold bridging. This occurs where there is a discontinuity in the insulation layers, typically at structural members or junctions between walls, floors and roofs. Thermal bridges have two principal negative effects. Firstly, they increase the overall heat loss by providing an easier pathway for heat to escape, and secondly, they create cold spots internally. Condensation and mold growth can occur in these cold spots, which has a detrimental effect on the indoor environment. The first of these, typically where structural elements like studs in a timber frame wall intersect the insulation, is accounted for by an adjustment in the U value calculation. If we consider a 140mm thick panel of rigid foam insulation, if we use this in a typical timber frame wall, the U value when adjusted to account for cold bridging at the timber studwork will work out to around 0.22. On the other hand, if we eliminated this cold bridging but used the same thickness of insulation, the U value drops to 0.15, purely due to the lack of thermal bridging at the studs. Thermal bridging at corners and junctions is accounted for using an additional value for linear thermal bridging, known as a psi value, but in most cases these are addressed using standardised pre-assessed details to limit heat loss. The easiest way to visualise the way thermal bridge-free design works in practice is to simply imagine drawing a pencil line around a cross-section of the entire heated envelope of the building. Maintaining the continuity of insulation can pose challenges in some areas, such as window reveals, where space may be extremely limited. In these areas, thin insulation systems like our Spacetherm aerogel boards can help ensure this continuity without sacrificing thermal performance. The other way we can optimise our energy performance is by paying careful attention to the airtightness of the building. By this we don't mean sealing up the inside entirely, but simply ensuring that the only air movement is air movement we can control via ventilation systems. Both the wind blowing and heat rising by convection internally can drive air movement, and this can dramatically impact the overall heat loss, especially as levels of insulation increase. Reducing this air movement is simple on paper, but can prove difficult in practice. Traditionally, air barrier membranes have been installed internally on the warm side of the insulation. Typically, these also function as vapour control layers to limit the ingress of moisture. This positioning requires the air barrier to be sealed at all surface and structural penetrations and remain sealed. If the membrane is damaged either during installation or by following trades or later refurbishments, for example, then both air leakage and moisture vapour ingress problems can arise. By moving the air barrier to the outside of the building, external systems such as our wrap-tight allow for an almost penetration-free airtight layer, which can be installed faster and more robustly. It's important to note that what we're talking about here is unplanned air movement. Planned air movement, provided by ventilation systems, is an important part of maintaining healthy air quality. So when we talk about airtightness, we really mean unintentional air openings and drafts. If we can rely on achieving a good air leakage result, then that can be fed into the SAP assessment calculation, meaning this good performance can be traded off against, for example, thicker insulation or more expensive and harder to source windows. For this to work though, we need to rely on those design values, and systems like wrap-tight can help ensure the building meets those targets once it's finished on site. Controlling and managing the moisture flow in a building is fundamental to maintaining the durability of the building envelope, maximising energy efficiency and protecting the health and safety of the occupants. There are a number of potential moisture sources affecting all building envelopes, the most obvious being the external environment, weather and rain. While buildings are designed to be weather resistant when they're completed, they can still pick up a lot of moisture during construction. The longer the internal fabric of the building is exposed during the build process, the more wet materials like concrete and mortar are used, the higher this moisture load will become. Once the building is completed, weather-tight and heated, this moisture can begin to escape, and this initial phase is known as the drying out period. During this period, this excess moisture must be able to escape without causing problems. So it's important a building is designed to accommodate this additional moisture transfer, over and above what might be expected when it's in use. If this moisture cannot escape, it may lead to condensation problems within the building. Condensation is the formation of liquid water when warm, humid air comes into contact with a cold surface. The warmer the air in an environment is, the more water vapour it can retain. However, when this moisture-laden air cools down, its capacity to retain water vapour reduces, and this vapour will turn back into liquid. This moisture can come from a range of sources, like cooking, drying clothes, even from building occupants breathing. The most common example of this is bathroom mirrors, where the warm air in the bathroom can support a lot of moisture, for example a shower, but when it hits the cold surface of the mirror it loses this ability, causing the mirror to fog up. The insulation in the building fabric helps keep the indoor temperature more or less constant, but as we move outward through the building element, the temperature will drop sharply across the insulation layer. As the temperature drops, the air loses its ability to retain water vapour. At a certain temperature, called the dew point, this air loses its ability to retain the moisture, and the moisture condenses. In our bathroom mirror example, this is inconvenient but pretty harmless, but say in a roof space, this liquid can cause timber to decay or damage any stored items. Cold spots in the building, either from poor insulation, cold bridging or drafts, can also cause condensation in the living spaces, and this in turn leads to mould growth, which can have adverse effect on the health of the occupants. Taking these factors together, it's very important that the management of heat, air and moisture in the building is carefully balanced, and the impacts of these are closely interrelated. We ran a webinar, Introduction to Building Physics, a few weeks ago covering this in a lot more detail, so if it's of interest to you, you can go back and check that out on our website or our YouTube channel. So having looked at the regulations in physics, it's now time to think about the building itself, beginning at the very bottom. The first part of work on site is the groundworks and foundations of the building. Groundworks covers the preparation of subsoils and dealing with any contaminants, while the foundations are what supports the actual building structure itself. Preparing the basic site is important, as not only does ground require to be levelled and cleared of vegetation or debris, but some sites can harbour contaminants, particularly if the site has previously been used for purposes other than housing, like former industrial sites. As well as determining the load-bearing capacity of the soil and rock on a site, care also has to be taken that the eventual structure is kept free of damp and water ingress from the soil, so an understanding of the water table on site is also important. Generally speaking, these issues can be determined by conducting what is called a site investigation report, which looks at the underlying geology of the site and any historical uses. It may also include borehole reading to measure the presence of any gases. There are four main contaminants we have to consider when assessing the measures necessary: methane, radon, carbon dioxide and VOCs, or volatile organic compounds. Methane is a naturally occurring gas caused by the decomposition of organic materials, and it's most commonly associated with former landfill sites. If it's not correctly managed, methane can cause headaches, dizziness and respiratory illness, but it's most commonly associated with being explosive. Carbon dioxide, or CO2, is an asphyxiant and typically originates in former mine workings, where pockets of gas can collect and be released by changes in groundwater levels or atmospheric pressure. Volatile organic compounds are things like hydrocarbon fuels or industrial chemicals, which may leach into soils and emit a range of harmful gases. These three types of contaminant are usually related to historical site usage, so it's relatively straightforward to identify if they may be present by studying the site's history. If any former uses may cause a problem, boreholes and monitoring can be used to identify any contaminants and classify the risk profile of the site. Radon is a little different in that it's associated with underlying site geology rather than historical usage. The necessity of testing for radon is therefore determined by radon maps, which detail where in the country radon-releasing geology is likely to be present. Once the contaminants are identified and the associated risk quantified, remedial measures can be specified. At lower levels of contamination, a simple barrier membrane is sufficient, but at higher levels, passive or active ventilation systems may be needed. It can also be possible to remove or chemically neutralise some forms of contaminants, an approach mostly taken with VOCs, such as, for example, on the site of a former petrol station where fuel-contaminated soil can be removed. Whilst it's not all that common to come across these types of sites in self-build, a membrane under the floor is still necessary to prevent damp and moisture rising through the foundations. This is called a damp-proof membrane, or DPM. Most quality DPMs will also provide a degree of gas protection at low levels of contamination. These are the foundations of my own home, where the DPM is being laid under the floor slab. This protects against moisture from the ground, as basic concrete is not necessarily waterproof. This DPM can be upgraded with foils or specialist films if required to deal with any contaminants on site. And whilst we use the Proctor membrane, which was an overspecification, this wouldn't have normally been required for my particular site. Here, the floor slab is poured on top of this membrane, and this type of foundation is known as a ground-bearing in situ slab, as the slab is fully in contact with the ground and is poured into place directly. Which type of foundation is used is determined by a range of factors, such as geology and the loadings from the building itself, the construction of which we'll look at now. The parts of the building above the foundations are referred to as the superstructure of the building. In traditional build, the upper parts of the house are made from brickwork and concrete blocks, with floors either being beams and blocks or timber joists. Homes of this type are constructed wholly on site, and this can be a relatively slow process as brickwork and blockwork takes time to lay, and concrete and mortar have to dry out and harden before additional works can be undertaken. As we discussed earlier, this slower process and higher level of wet trades means moisture loads may be a lot higher and must be carefully managed. Traditional builders, however, are very good in terms of thermal mass, which is the building capacity to store heat. This means it takes this type of building longer to respond to changes in the heating or cooling conditions. If the structure is heated to a constant temperature continuously, this can be of benefit to its energy efficiency, but if not, it can mean the building takes much longer to warm up or cool down. Another type of structure used is timber frame, and this is the most common method used in the construction of kit homes. Homes of this type use timber panels and floor cassettes constructed in factories, which are delivered to site and then can be erected very quickly. This gives a basic wind and watertight structure comparatively quickly, and the building can then be fitted out with services and finishes. Things like insulation are usually added after the building structure is up, in what's called open panel construction, but sometimes the insulation is factory fitted too in a closed panel frame. The studs in this type of panel are the main load-bearing members, transmitting vertical structural loads, which the sheathing boards prevent the studs from twisting and moving. These studs can, however, act as cold bridges, so panels like this tend to be thicker, as this effect must be counteracted. The main advantage to this type of construction is the ready availability of suppliers and contractors, giving a competitive market and wide choice of systems. The last of the most common methods of house building is a structural insulated panel, which is the type of construction my house used. A typical insulated panel comprises of timber sheets, usually OSB, sandwiching a core of rigid foam insulation. Because these panels are not bridged by any less insulating structural materials such as studwork, they can match or exceed the thermal performance of a traditional timber frame wall with substantially less thickness. There is, however, scope for problems to arise if project requirements are not fixed and tolerances on site are not achieved. SIP homes must be designed and manufactured well in advance of their arrival on site, and it's very difficult to account for any changes during the build process. SIP systems also rely on the use of blown foams and manufactured timber products, so may not always align with project requirements if a more ecologically focused build method is required. SIP systems are typically built by specialist contractors, in the case of my house here, utilising a Kingspan Tech panel to achieve both very low U values and an almost completely thermal bridge-free design. The roof and wall panels here achieved U values of 0.14 and 0.17 respectively. The thermal bridging heat loss, or Y value, was only 0.029, dramatically reduced from the 0.15 standard value, which combined with the very low air leakage rates helped deliver to the EPC A ratings. The use of wrap-tight externally delivered an air leakage rate of 0.64 metres cubed per square metre per hour, well below the Section 6 maximum recommended value of 7 and in line with best practice. This performance helps deliver a carbon dioxide emission rate over 30% better than required. This also gives EPC ratings of 94 for energy efficiency and 93 for environmental impact. Timber frame and SIP constructions typically use a range of different membranes to protect and enhance the performance of the base constructions. Usually there is a membrane fitted either side of the wall, a vapour permeable or breather membrane on the cold side of the wall, and a vapour control layer on the warm internal side. The basic function of a breather membrane is to keep the timber in the structure dry during transportation to site, and until the final weather protection layers of the building are added. This not only reduces the moisture loads on the building, but helps ensure effective drying can take place later on. This can be thought of like a Gore-Tex jacket for the building. It keeps the rain out while allowing vapour from the building to escape and dry out. Our frame shield membrane fulfills this purpose and has been used in timber frame for over 30 years. This basic membrane can be upgraded to perform various other functions, however. The first of these is to add a reflective layer to the membrane to improve the level of insulation in the building. This reflective or low emissivity layer restricts the flow of heat energy by radiation and enhances the U value of the wall element. Our Reflector Shield TF membrane is the highest performing membrane available today. The second option is to make the membrane airtight, which reduces the building's air leakage rate, giving further enhancements to energy performance. Our wrap-tight membrane, which combines this airtightness with a simple and fast self-adhesive installation process, makes this possible by sealing the building from the outside, well away from any switches, pipes or cables which might otherwise have to pass through the airtight layer. On the other side of the wall, vapour control layer membranes help limit the ingress of water from the warmer and more humid areas to the colder outer parts of the wall, reducing the risk that condensation will occur. A basic vapour control layer, such as our range of ProCheck membranes, will perform this function, while also, provided it's fully sealed, limiting air movement. As with vapour permeable membranes, however, VCLs can be upgraded in various ways. Our Reflectitherm Plus material adds a reflective coating, similar to that on the Reflectishield TF, in order to boost the thermal performance of the wall. To do this effectively, it also requires an airspace adjacent to the membrane, and this space also provides a zone to run services, helping to reduce the amount of sealing required around sockets, switches, and other building services. The final type of vapour control layer is a variable resistance VCL, sometimes called an intelligent membrane, such as our ProCheck Adapt. This material varies its resistance according to the environmental conditions at any given time. This membrane becomes more resistant to vapour in the winter, when the condensation risk is at its highest, and less resistant in the summer. This allows the warmer external temperature to dry out the building fabric effectively, offsetting any build-up of moisture that may have occurred over the winter. My house used Wrap-Tite externally and Reflectitherm Plus on the inside to limit the air leakage as much as possible. This not only assisted with meeting the targets in the building regulations for overall energy performance, but also ensured the mechanical ventilation and heat recovery system were able to operate optimally, ensuring good indoor air quality while minimising space and heating costs. The final part of the building envelope we must address is the roof, and there are several common types of roof and even more factors to consider when designing one. Flat roofs, despite the name, are not strictly flat, but pitched at 10 degrees or lower. They must have some degree of pitch in order to ensure rainwater drains adequately. Most flat roofs today are of warm deck construction, which is where the insulation and waterproofing sits over the structure. The roof joints and structural decking are therefore kept well above the dew point temperature, making this kind of roof far less prone to condensation issues. Because the insulation is usually unbridged, they also maximise the thermal insulation performance. Although flat roofs and low-pitched roofs are a common feature of contemporary designs, more commonly homes will have pitched roofs, and these fall loosely into two types. Warm pitched roofs, in which the insulation follows the slope of the roof itself, and cold pitched roofs, where the insulation rests on the horizontal ceiling, with a cold loft space above. Traditional UK practice has been to follow the latter model, but it's becoming increasingly common to use warm roof construction. The common structural elements of a pitched roof consist of trusses or rafters, over which are laid an underlay membrane, then battens and tiles or slates as the final waterproofing layer. Some types of roof, and most roofs in Scotland, may also include a sarking board over the rafters, with the membrane laid on top of this. This stiffens the structure, making it more resistant to wind loads, and also facilitate the traditional Scottish roof practice of fixing slates directly to the sarking boards. If battens are used on the roof, there must be a gap to allow drainage under the tiling battens. This is achieved by either draping the underlay between the rafters or by using a counter batten to lift the battens up. Whichever type of construction is used, ensuring the roof remains free of condensation is critical to long-lasting, trouble-free roofs. Historically, this was achieved by adding ventilation to the roof to flush out the moisture before condensation could occur, but this is increasingly being replaced by vapour-permeable underlay membranes. These membranes allow moisture to escape through the entire surface area of the roof, meaning there's less chance of a ventilation opening being blocked or incorrectly fitted, and simplifying the overall design. In a warm roof construction, our wrap-type membrane is ideal to ensure vapour can escape while limiting air leakage. The roofing membrane can simply be wrapped onto the walls and sealed to provide an effective air barrier around the entire building. In cold roofs, our roof shield has a proven record for over 25 years in keeping roofs trouble-free by not only allowing a high level of moisture transfer, but also by permitting air movement throughout the unheated loft space, making the formation of condensation almost impossible under normal conditions. So hopefully that's given a good overview of the basic design considerations in building a house, and there's a lot more detail on all of these factors available in our webinar series at www.proctorgroup.com or here on our YouTube channel. Even being involved in the industry, building my own house was a learning process as to how all the systems and trade involved interact and how to best manage the processes. Developing a good understanding of the issues and compromises inherent in the construction projects and a good relationship with all the parties involved in project delivery really is the key to self-build success. We'll now move on to the Q&A session. Good morning, everyone. Welcome to what is our 11th webinar in the series that we've been doing from the start of lockdown. what we see is starting to come out of lockdown. So I hope you find it interesting and educational. As always, we will stay here as long as we need to answer all your questions. So please feel free in the YouTube feed. You can also email us at webinar@proctorgroup.com. Please don't email website@proctorgroup.com. They won't be picked up during this chat. So please email webinar@proctorgroup.com, or you can DM us on Twitter @proctorgroup. After the webinar, you can go to the Proctor Group website /webinar, so www.proctorgroup.com/webinar, and there you can request a sample pack regarding some of the products that we've talked about. You can watch a replay of the webinar, you can request a meeting to go through your drawings, etc. with your technical team. There's a lot of information that you can get there, and you can also download a personalised CPD certificate on that site as well. Last couple of things, you will receive an email after this which has a link to the survey, so please fill it out. I've already seen some interesting comments coming through on the chat, so if we can't get to all of those, and some of them are just general feedback, please, if you fill out the survey, we read it all, I read it, and we do take the comments on board and use them for the next webinar. Our next webinar will be in 2 weeks, same time, 10 a.m. And the topic is Introduction to Building Physics, Heat, Air and Moisture Movement. So essentially it does take some of the elements that the self-build covered, but in a lot more detail. We did one, the first webinar we ever did was on this topic. So this one will be slightly different, but in the main very similar, with another live Q&A afterwards. So a number of people may have missed that first one, so please feel free to join. Really helps us if you give us a thumbs up on the YouTube thumbs up bit, for want of a better word, and also you can subscribe to our channel if you want to see some of the future content we'll be putting out. I think that's it. As I said, if you can register for the next webinar now, that is live on the webinar page on our website, so we hope to see you then. Some quick introductions. You may have seen some of these faces, a number of the webinars we've done over the past however many weeks that have gone so quickly for everybody. Sue Menmere, if you just give us a wave and say hello to check everything's okay, Sue.
Hi there.
Great, Sue's been with us for many years, part of our technical team. Ian Fairnington, I just heard him. Sorry.
Morning.
Good, great. Ian is our technical director based up in Bulgaria in Scotland, and John Johnson.
Morning, folks.
Morning, John. John is our national sales manager and also looks after a lot of our timber frame customers, so knows an awful lot about offsite and the products that we use within that. And I'd also like to introduce Allan Corfield. Allan is an RIBA chartered architect, and he's actually overseen not only my house, which I'm sitting in, so thank you, Allan, but he's overseen over 350 low energy projects and homes across the UK. So I think Allan now has a team of around 15, so it's grown considerably over the years. And he really is an expert in the modern methods of construction. So, you know, he's a member of the Structural Timber Association, Passive House Trust, NACSBA. And I think, Allan, you still have your monthly column in the Home Building and Renovating magazine. And you do a lot of talks at these home building and renovating shows, one I know which is coming up. Is it next month? I'm trying to remember.
Yeah, the first, obviously, because we don't have actual shows anymore, not this year anyway. We've got a virtual show coming up on the 24th and 25th of July. So
okay. So this month, sorry, excuse me. So as I said, Allan's kindly accepted my invite to join us today. So we thought it would be good. This is the first kind of special guest on video we've had. We have had experts talking verbally on different webinars we've done in previous years. But we thought it would be good for this audience, and we've already had some questions in via email which are more associated with the kind of self-build process, which hopefully we can ask Allan. So as I said, if you have questions, please start posting them on the chat. If it's just generic comments, that's fine. We will address them if we can, and if we can't, then we are happy to see the opinions of. But again, to just reiterate, Proctor Group, we really are experts in the membranes and more the building physics and that side of it. So when it comes down to self, there's an awful lot of personal preferences, and of course, I learned that building my own house, the type of the contractor you use, whether it's architectural or designers, and I think it's fair to say there a lot of different types of designers can help you with all this. It's not just limited, of course, to architects, which I think has been noted on the chat. So yeah, duly noted. Again, that comes down to your personal preference and how you wish to do things. So I will just start with the questions because they're coming in quite thick and fast, and I will try and get caught up with the YouTube feed. So please bear with me. So if I can just start with one that came on fairly early in the chat, actually, I think it was from a James regarding roof shields. He just did a new build for a client. He used roof shield for condensation reported. So let's get this one addressed if we can.
Okay. I mean, like, it would actually be very, very unusual to have an issue with condensation when using roof shield on a roof. It's just not something that we generally come across. As the webinar actually explained earlier on, there is a lot of moisture in a new build house, especially if you're using like traditional methods, if there's plasters, cements, renders, etc. So that moisture has to be able to escape somehow. The roof shield, because it is also air permeable, will help facilitate that drying out process because you do get the air movement, which is all beneficial in that way. But obviously, if James wants to get in touch with us, about his project, then we can obviously look into that a bit more closely for him.
Okay, that's lovely. Thank you very much. Ian, if I can come to you, please. One that we've had in from Josh via email. I'm currently looking at the design of his new house and wishes to strive for an energy efficient home. In fact, this is actually, I think, yeah, coming through in the chat as well. Design with lots of insulation and seems to be everywhere, but worried that I'm losing space. Is there any alternatives?
Yeah, it's a typical question. Everybody wants to put lots of insulation in, and sometimes the amounts and thickness of insulation that you put into a building can be quite frightening as you lose floor space as you insulate further. One of the best ways, which we show on our website, is to improve the air tightness of the building, which doesn't have an effect at all on the footprint. You're just replacing the breather membrane with an airtight, self-adhered membrane wrapping around the building, similar to you did on your project where you improved the air tightness. That can have a massive effect. So it can be, sometimes when you get down to very low U values, it can be the equivalent of taking your air tightness from a level of 7 down to 1, can be the equivalent of putting in an extra 100 millimeters of insulation. So by improving the air tightness, you're looking after the building envelope from a condensation point of view, moisture point of view, but at the same time, you're improving the energy efficiency of the building.
Okay, great. Thanks, Ian. Alan, Joe's asked on YouTube, what are the biggest mistakes self-builders make? And what are the top tips for someone like myself who's building a house?
Well, there are, anybody that's watched Grand Designs will know that there's well publicised mistakes, and Grand Designs isn't a true reflection. I think somebody had commented about the bad press that self-building construction's had. So there's lots of things that you can do to start with, and most of the mistakes that we find come very early on in a project. So simple things like not assessing the site before you buy it. You mentioned about the foundations. You can't accurately budget for a build without checking the ground conditions for bearing capacity, so knowing what the foundation system's going to be, or actually having how can you get power onto your site. If there's a telegraph pole in the next field, isn't enough review to make sure that you can actually get power to it. And we've had quotes for new power from anything from $5,000 to 120k. So that's a tiny little thing that somebody can do at the very start to check. The other thing that we mentioned is budget. Before you speak to an architect, before you do anything, you must look at your budget, both in terms of the total amount of money you can and you're willing to spend, but also where that's coming from. Most of the people run into problems on Grand Designs not because they've actually not had the budget, it's because of cash flow problems. You have to know where the money's coming from, how it's going to be done. So these are simple mistakes. A lot of these can be worked out very early on by getting a proper assessment of the site, which an architect should be able to help you with. Creating a brief, spending a lot of time. You and Ian were really good at going through what you wanted to do and what you wanted in the house. Because if you were going down the self-build route, it is a challenge, but it's worth it. But you're getting your dream home at the end of it. So that's the key thing. It's yours. It's tailored specifically for you, for your site. So spend the time with your family working out what you want in your home and how you're going to use it. Think of the top 5 activities you do, and how your home can facilitate that. Try not to make changes once you're on site. Freeze the design. You've got a lot of time up to that point, so just make sure you use that well, and invest in the fabric. The whole point of what we're talking about today is the improvements and betterments that your amazing products can help with on the fabric of a building. And it's that forever bit. It's working out the design properly, using the sun that we have, but also making sure that we don't have too much for solar, for overshading, things like that we need to take into account. Use the sun, use the solar design, and get the fabric, the forever bit of your house right. So invest in that up front. So there's some things, key things that you can fall down on, but also things that are quite easy to sort out at the very start.
Good, thanks, Alan. Really, really useful. Yeah, and I would agree. Planning at the start, how you're going to use your home. I think this lockdown period has taught us personally, both being in the house, working full time for a long time. We had a big negotiation, my husband and I, and it sounds a bit spoiled between he wanted a skylight and I wanted a cinema room towards the end of the project. And we did put in both a very cost-effective cinema room and the skylight. And I think both of those have come in extremely handy during lockdown. But yeah, I would agree. And where you're going to be spending time and what you're going to actually be using the house for is a really good point that a lot of people don't think about. So, good. Okay, Sean has asked, yeah. So did we use MVHR? We did, Alan, and you designed MVHR into this house. Which again, I'd heard a lot of rumors about, not having been directly involved in MVHR. Is it expensive? Is it noisy? Is it, will it feel drafty, or does an airtight house not feel drafty? And I think I've been really pleased. I think with the right research and support from others, we were able to choose a system which, is inexpensive. It's not noisy. It does allow adequate airflow throughout the whole house, and never has it felt too airtight or too drafty at any point. So having grown up in quite a drafty house, you put a jumper on and the parents kept the heating off. So we were quite used to living in an old house. It's been really quite comfortable. So it's good. John, if I can come to you for one, please. Joseph has asked, I have a steel beam running through to the outside. How do I prevent condensation forming on the steel? Okay,
that's a good question. And it's one that we do come across quite a bit. We've supplied quite a lot of our wrap therm, which is the wrap tight product with the aerogel, space therm aerogel in strips. So we can supply that into the actual steel beams, either in sheet form, or we can have it bespokely cut to the exact sizes of your steel. So the wrap type being self-adhesive. So on the back of that, you would have your strip of space therm. So then it'll allow it to wrap into the steel. And this product being airtight also has an added benefit. We can supply in full sheets that you would cut on site yourself, but you've got a bit of wastage on that, and it's not the easiest product to handle. So knowing what lengths of steel you've got, exactly which areas you want to insulate, we can have that prefabricated and cut exactly to the designs that you require.
Okay, that's good. Alan, maybe one for you if you could help with this one. Allan Corfield's asked for a general ballpark steer on build costs. Something you can...
$1 million question. It really depends. So it is dependent on a couple of things. So floor area, specification, how efficient the design is, because the same floor area on a rectangular building will cost a hell of a lot more if it's in an H-shaped building that's not designed to standardized sizes of materials. And your procurement route, i.e. how much work are you putting in? So without being too slopey shoulders about it, you can build, and a lot of people are trying to aim for, and in the self-build, and what we class as the majority of self-builders are people that are managing their project and they're appointing individual trades. So that's what a lot of the self-builders are doing in the UK. You can build at that point from anything from £1,100 to £1,400 a square metre. Sorry, I know the question was asked in square foot, but that's that's lost on me. So that's a guide, a very loose guide, but it really depends on the efficiency of the build and the design. That helps.
Okay, that's great. Thank you very much. Ian, if I can come to you, please. From Josephine, I noticed most roofs seem to be a cold roof design. Is it worth looking at warm roofs?
Yeah, it's a great question. It constantly baffles me. When I started with Proctor's a few years ago now, over 20, the cold roof design seemed an antiquated way of building, and I was told that everybody would be building warm roofs within 5 years. But yet still now the cold roof is still the most popular way of building in the UK. But to consider the warm roof design is a very good way to look at things from an energy efficiency point of view. You're using the full volume, your building envelope is fully insulated, you're utilising the envelope space very well. So I think the warm roof is a very good way to look at things. You have to be careful designing a warm roof. It's not possibly quite as easy as a cold roof. But if you insulate well, take care of the air tightness as well, and your moisture control, then a warm roof can be a very effective way of designing a roof system. We utilise Wrap-Tite on our warm roofs designs. It's got a BBA certificate, so it improves the air tightness on the envelope while still allowing moisture to escape as necessary. So that would be our advice.
Okay, and this kind of links in with the question that Matthew's asked on YouTube. He's looking at a room partly in the roof, so part warm roof, part cold roof. What's the best way of ventilating, or does he need to, is the question, I suppose, and which membrane would we recommend for that?
Yeah, that's a less straightforward answer to that one. We probably have to look at the designs, and we have very good people at head office that can have a look at the design, because to combine the warm roof and the cold roof can be quite difficult. Generally, we have our membrane roof shield, which can be fantastic for cold roofs and ventilating dead spots within the roof. But if we've got a warm roof, we want to maximise it with the energy efficiency of Wrap-Tite. So really what we'd like to do is have a look at that drawing and see exactly how it works and what would be the best membrane to look for. But we will have a solution, but we need to be more specific of the drawing. Okay,
that's great. Thank you very much. Sue, if I can come to you, please. This is one we've had on a couple of the webinars, actually. Jim has asked, mentioned, my timber kit was erected just prior to lockdown and it has reflector shield on the outside. Does this need to be replaced? Obviously, the exposure times are longer than they have been usually.
Yeah, absolutely, just now anyway. Typically, what we would normally say with these types of membranes is that they really should be covered within 3 months of being exposed. However, last year we embarked on a long-term testing program where we had our membranes exposed for up to 12 months out in the open. These were tested periodically every quarter, and what we found was that after 12 months exposure, the actual performance of the membranes in terms of the vapor permeability and air tightness, etc., were not actually affected at all. With reflector shield, obviously, the longer it is left exposed, it becomes more susceptible to mechanical damage. So what you would need to do is obviously go round the building, check it for damage, just to make sure that the reflective surface has not been affected at all. If there's any sort of like small bits of holes, tears, etc., they can be replaced quite easily just with a little patch over. But it gives a degree of confidence that once the external cladding's up, the membranes will perform their function as they're designed to do.
Okay, that's great. Another one in from Colin. Okay, I think it was more directed to me. I'd be interested to know if your house suffered from overheating this year. With no thermal mass, we'd hope it to be hard to keep it at steady temperature over the summer. So yeah, so he's saying basically the benefits of thermal mass mean the building is comfortable in the winter and the summer due to the thermal stability of the building. So we didn't really suffer from overheating. I don't know, Alan, if you can help with anything in the design that helped our house with that, because we do have a lot of glass. And again, the glass we got from a company called Lumi, an Irish business, which is frameless, and it's really good stuff and good performing glass, whether that's had a benefit, but it's not something that we've struggled with. Alan, can you help with that one a little bit?
Yeah, so you do have a good bit of thermal mass in the plasterboard and also in the way that the slab was designed. So that is taken into account, and thermal mass isn't one of the biggest, or it's not prevalent in SIPs construction or timber frame construction, but there's other ways of providing that in a build. So that was all looked at as part of the design. And also in the SAP and our ArchiCAD software, we looked at the potential for summer overheating. And again, you can design that, you want to design that so that it's dealt with outside the building, so it doesn't come in, so you don't have to deal with it mechanically. But the only real way, even when we design passive houses, is purge ventilation, so opening the windows and getting airflow across the building. But it's good to hear that the effort that went into making sure that didn't happen was right. So it has to be done in design, really.
Okay, great, thank you. Just trying to go through here, anything else coming through on the YouTube, bear with me. Okay, let's have a look. How did we control the quality and installation of SIPS panels on site, including fixings between panels and onto wall plates to resist pull-out forces? Again, I'm not quite sure to direct that one to, maybe an Allan one, because you're very familiar with SIPS, aren't you?
Yeah, so that was designed so that all of the SIPS companies that we use have got their own in-house engineers that design for that, and all the fixings are specific to SIPS. So the long SIPS screws are worked out and designed so that through the OSB and into the structure, those forces are taken into account. So it's a standardised item at regular fixings, all specified by the engineer. So it's something that's just taken into account, and the team that are on site have got loads of different, or they've got very strict instructions on the fixings that they use. So it's something that's just taken into account at the design stage and then followed through on site. Okay, good.
And the speed of construction with SIPS, I was quite shocked at. And I remember the building went up very, very quickly, and Allan said to us, that's the quick bit. So just prepare for the wait now, and he wasn't wrong, but it was good. So coming on to a question, John, if I can come back to you, this is about a SIP house actually. If I'm building a SIP type house with SIP roof panels, what would be your recommendation for a suitable membrane?
Yeah, that's a good question. It would depend really on what the roof finish is. A lot of the self-build projects, they're looking at various types, slate, tiles or metal roofs. So Wrap-Tite is really the best product for that, because as Ian mentioned earlier, putting the thermal mass to the outside of the building and your insulation, and you eliminate your condensation problems. So Wrap-Tite, yeah, that would certainly be the product for putting that product onto. It means that the trades can work below the building, because the building is then more or less watertight, although you need to cover it up as soon as possible. But being self-adhesive, there's not issues with it flapping around in the wind. So Wrap-Tite would certainly be the product that we would recommend for that.
Yeah, and interestingly, when of course we used Wrap-Tite on the walls and roof, of course, but during the construction, which was in the winter, the guys working inside the house, so once the frame was up and the whole thing was wrapped in the Wrap-Tite, we basically just wrapped all the open windowing coverings with it as well. So leaving the self-adhered bit just straight into the face. And they were all really cozy. So that's one thing that all the contractors have said, we've never worked in a house that feels this warm. So of course, with the insulation, the structural panel there, and then you've obviously got the complete weather protection, and the air tightness of the Wrap-Tite externally really stopped that draft coming in when they were working. So I know it's not a huge benefit to your long-term self-build, but even just keeping the trades and everything dry whilst allowing that drying out when all the work was happening internally, it was a benefit I hadn't thought of historically before the build. So.
I think, okay. Can I just interject just on the added bonus of the membranes? And it was picked up on do I have to replace the membrane if it's been outside? We regularly, because self-build can be there can be stops and starts, and sometimes it's not quite as well planned out as a main contractor site, that there can quite often be a time gap between the external facade going on. So we regularly have upgraded to Reflector or Wrap-Tite, because in our experience, it gives the client that bit longer exposure. And it's great to see that you're going to have you're going through the formal testing of that. But there's loads of added bonuses, and the one you picked up on, a lot happier builders working inside in a sort of 15-16 degree building site with no heating inside. So there's a lot of added bonuses. So
yeah, absolutely. Thanks, Alan. Okay, good. Sue, here's one on ground gas, which is an area you're familiar with. So my site has a carbon dioxide risk on it, and I was looking at Protect GM Super. Okay, great. Does he need a separate damp-proof membrane?
Simple answer is no. The GM Super, which is reinforced polyethylene with a foil core, will act as the damp-proof membrane, as well as protecting against carbon dioxide, radon, and methane. So no separate DPM is required.
Okay, that's great. Thank you, Sue. And Alan's asked on the YouTube feed as well, foundations in our slides showed a ground-bearing concrete slab. Did we need any other substructure in your house as well? As we would be unlikely to get away with just a slab on our London projects. Is that something you come across, Alan, London projects with just a slab?
It really depends on the ground condition. So our sort of preference now is what we call a passive slab. So we insulate everything underneath, and then we cast a ground-bearing slab with almost a ring beam round it. But it's completely dependent on the ground conditions specific to that site. So you get your SI done, your engineer checks and checks what the bearing capacity is, and then the foundations are designed around that, because it can be anything from piles to traditional strips, but it's really dependent on ground condition and how much insulation and energy performance you want to get from below the DPC effectively.
Okay, that's great. Ian, one for you on cold bridging from Rashid. I have lots of insulation with my build, but now reading about cold bridging, is it important I have lots elsewhere? So I think he's talking about the overall build, and obviously he's got quite thick insulation and concerns about the cold bridging.
Yeah, I think it was obviously discussed in the seminar that you've got to watch out for the thermal bridging, and it can have a detrimental effect to the overall insulation efficiency of your building. It's quite common to actually think, if I'm putting lots of insulation elsewhere, does it really matter? But it can have such a big detrimental effect. If you're insulating a lot in the walls elsewhere, then it highlights even more that cold bridge. One of the common areas is window reveals, where people think that they're putting lots of insulation, in particular in refurbishment where they're using internal wall insulation. They think they could put lots of insulation internally on the walls, and the reveals, well, it doesn't really matter too much. But studies have shown, UCL did some great studies along with Chris Sanders on the effect of the reveal. And effectively, the research showed, depending on the size of the window, that 140 millimeters of insulation on the walls without the reveals being insulated was the equivalent of 60 millimeters of insulation if you do insulate the reveals. So it showed quite dramatically the effect of insulating what you think is just a small piece, and it doesn't really matter how it can actually affect the thermal performance. And you've also got the cold spots, which was mentioned during the seminar earlier, that the cold spots can increase your condensation risk. So you need to be dealing with them anyway. So it's a good measure to take care of your thermal bridging to improve the energy efficiency.
Good, thank you very much. Let's have a look here. So there are still some more questions coming in. Oh, here's a good one. John, we'll go with you because I know you've got a jacuzzi at home. In the garden. What membrane would you suggest if I'm building a sauna or steam room within the house?
First of all, you've got to get the wine rack ready.
Agree.
Yeah. We had that recently on a project up above Glenfarg where they built a steam room, and it was a Profoil 861, which is our a reinforced vapor control there. It has an aluminium core through the inside of it, so it's ideally for use where you've got high humidity, ideally for swimming pools where you've got the chlorine, and the foil's protected by 2 layers of polythene either side and a layer of reinforcement. So that would certainly be the product that we would utilise and recommend if there's any high humidity areas in a new build or self-build.
Okay, good. Thank you, John. Sue, if I can come back to you here, one about sort of the designs that we've offered, or do offer rather, looking into a self-build project and wonder what services you supply, i.e. could you do my U-value or SAP calc?
Okay, we don't provide SAP calculations. However, we can provide the U-value calculations which feed into that. Other services that we provide would be condensation risk analysis, WIFI analysis if appropriate. We will obviously check specifications. We can offer, certainly at the moment, video conferencing with, sort of like our sales managers, for example. And again, with installation advice as well, we can be there really pretty much from every step of the process.
Okay, great, thank you. And SAP calc, Alan, is that something that generally the designer would carry out then?
Yeah. So some architectural practices will do it in-house, or they'll go to a specialist company who quite often do the SAP calc, issue the EPC, and do the air test as well. So it's just really important that the SAP exercise is done as part of the design, and always remember that the design, what you put into the design SAP calc, you then have to go and buy and put into your build. So have a cost sheet open to make sure that the stuff that's going in there you can actually afford. And we have it quite often where people have very tight SAPs if they're needing to get an A, that it's very, very tight, and you need to make sure that you follow it on site and you follow it through on site, specifically for air tightness. If you put in a really low air tightness value and then don't follow that through with the detailing and everything on site, that you can cause yourselves problems. So it's an interesting one, but make sure you use somebody who's done it lots of times.
Good. Okay, great advice. Thank you. Coming back to the last few questions, so if you have any more, please post them now. I think we've got 3 or 4 left. So Ian, if I can come to you, Paul has asked, can the building design be too airtight? Something we get asked quite a bit. I don't want to feel like I'm inside a plastic bag. I know I talked about our home earlier, but do you want to add a bit to that?
Yeah, it's a common perception that if you build the building too airtight, I won't be able to live in it. And obviously, designers like Alan, people like ourselves, don't want to live in a house that you can't breathe in. So you can't build it too airtight. The old adage of build tight and ventilate right is a very good concept. So you build tight, you avoid unwanted air movement, but you also take into consideration ventilation systems, which obviously you've done it on your house. You've built a very airtight house, and that's good design. So you should take into consideration the ventilation system to ensure that you don't build it too airtight if you haven't taken into consideration the ventilation requirements. And the old classic of opening the window, it's still okay to open the window, and there's still lots of people will only sleep in their bedroom with the window open. So people have spent lots of time building airtight solutions, energy efficient solutions, but the people will still leave that window open for their own purposes. So build tight, ventilate right is always the best concept.
Okay, great, thanks. I missed one that came through earlier from Ensign Design. If you don't mind, Ian, having this one as well. What membrane or membranes would you recommend, if any, for a Pavatex wood fibre insulated building with a lime plaster finish internally?
That's an interesting concept. I mean, obviously, if they're using the Pavatex and lime plaster, they're looking at breathability of the building envelope, which is a good concept. So you have to be careful and make sure that you are maintaining that breathability throughout. So the external facade of that will be important as well to ensure you're getting the air movement. And it's a brilliant project for Proctors to get involved in because of our HAM principles, which we've done a previous seminar on. We can look at the heat, the air and the moisture movement within that building envelope and decide which membranes we can do. We can do membranes that breathe, membranes that stop the vapour, and we can have variable membranes as well. So depending on the construction, we'd like to probably do a WIFI calculation on a project like that and decide which membranes is the best given that construction.
Okay, brilliant. And Ian, just one more, sorry, just because you're on a bit of a roll here, I'll keep picking on you. Can you, Dorel's asked, how do our products work with concrete panel systems and ICFs?
Another interesting envelope question. It's a subject we actually dealt with in BS 5250, the control of moisture draft that is just went out on Friday there for public comment. I chair the wall section of that standard, and ICFs and concrete frame did come into the debate quite a lot. ICF can be very good from an air tightness point of view, from a moisture point of view, in its own right. But controlling that condensation, moisture movement can be very important. And again, without coming back to, please speak to us further, we probably want to speak further on that particular project because it's an interesting concept. It's a really good concept to use, but we'd rather look at the actual technicalities of each particular project and then advise on that accordingly. Again, we can use vapor controllers, breathers, airtight breathers, or a combination.
Okay, good. And Alan, a couple here which are more kind of linked to the self-build side. Someone said, is it important to work with a specialist self-build practice in particular?
I think it's probably, given some of the comments that were on earlier on about architects and who's involved, I would sort of add to that it's not about the title, it's about working with somebody who has the experience and the knowledge to help you in whatever it's going to be. So work with an architectural practice. I employ architects, technologists, technicians, passive house certifiers. So we all have our place in it. And there's engineers and cost consultants and QSs and building surveyors involved in every project that we look at. But as I say, it's have they had the experience? Don't presume that all architects or designers have worked on low energy or passive house. It doesn't magically happen. You've got to detail everything, calculate it, and go through the training. So it's important to work with the best professional that you can. And I think the thing that we do slightly different is we try and help educate our clients and guide them through the process through the content that's on our website, our ebooks and our newsletters and the videos that we put out. Self-builders are slightly different clients because they need a little bit of help, education, and then let loose because the self-builder spends far more time on their project than anybody. And it's then being at the end of the phone or on a site visit to help out. So slightly different dynamic than your normal commercial sort of main contractor architect relationship.
Good, and we can certainly have some grand ideas that maybe we don't realise the costs of. But I think, I know there were some comments earlier about, self-build has a bad reputation about being able to keep to the costs. And I think that, yeah, it does have a bit of reputation, but it's also a little bit unfair because in my experience, it is possible to build within a budget. Where it became a little bit more challenging for us is as you're going, you get some of these new ideas and you think, what about a skylight? What about a cinema room? So if we hadn't have had these, luxury additions, then we would still be able to, we would be in a better financial position. But it does grow arms and legs. And I think that's one of the good things about having someone who can help guide you along that process because they can say, oh, hold on, this is actually the realism of what that's going to look like.
I think it's been mindful of that things have a cost and a value. And it's okay to spend money on things that will add wow and features to you. You don't want to be spending it in hidden pieces of structure that aren't there because it's been designed wrong, or another one big thing that we think of is that there's if you move a wall or you ask your architect or designer to make it slightly bigger, don't be surprised then that that's added to the cost. So it's both client and architect, or client and designer, that and you have to be strong enough in the relationship to go back and say, well, actually, obviously that's going to cost more money. Or so it's and one of the key things that when I speak for the magazine, we find out that a lot of people haven't worked out their budget in the first place, or they've never told their architect how much money they've got to spend. But conversely, there are a huge amount of bad press for architects who design a building, it gets costed, and then it's £100,000 more expensive. That's just not right, and it shouldn't be happening. So,
great, good, brilliant. Okay, I think that's all the questions. If I have missed any, apologies. We will come back to you if they've been sent via email. If you want to follow up with us, then you can email webinar@Proctor Group or reception@Proctor Group. As I say, we've got technical team working and sales team who can help answer any of your questions, have virtual meetings. And my cat's woken up, sorry, he's a vocal guy. So we do have our next webinar in 2 weeks' time, which will be an introduction to building physics, heat, air and moisture movement, which is a lot more in depth about some of the things that we've been talking about today, and across a wider range of types of buildings, not just self-build. So if you go to our website, www.proctorgroup.com/webinar, you can register now for that webinar next week. Please give us a thumbs up on the YouTube if you can, or subscribe to our channel for our cat's my debut for our next webinar. And I just want to say thank you very much to the people that were involved in, sorry, I have to move this cat, I'm so sorry. The joys of live shows, my apologies. Thank you very much to the Proctor staff that put this webinar together. You know, they're really great quality, and a lot of work goes into preparing these and getting them ready, you know, every couple of weeks. So it's fantastic. And thank you for answering the questions. Everyone, I know it's not easy when you're live and you don't know the content. And a special thanks to you, Alan, because, you know, this is different type of audience than we actually sell to directly. So we're more business to business, but of course our products end up in these projects. It's been great having your expertise. So thank you very much. So as I say, you will receive an email after this, so you can put your thoughts on the survey, you know, what we're doing well, what we could do better, and any comments that you have, and we'll come back to you. And we look forward to seeing you in 2 weeks' time, and I hope everyone has a lovely weekend. Thanks very much.